Our second method for getting a molecular formula out of experimental data is combustion analysis. So we've not yet talked about combustion. Combustion is a reaction with O2 gas that produces carbon dioxide and water. So you will learn how to balance combustion reactions in the next module. What we're going to do here is use the information that you get out of this reaction to figure out what was in our original compound. So like with elemental analysis, I'm going to give you the strategy, and then we're going to work through an example. So the strategy, we will be given some amount of carbon dioxide and water. So step one, we'll find mass of carbon from the CO2, and we'll find mass of hydrogen from the H2O. Step two, we'll need to find the mass of oxygen. We cannot find it from the carbon dioxide and the water, which I'll do a little example within the strategy step to show you why. But in order to find it, we do need to start with information about the sample size. So the entire sample, if it's made up of only carbon, hydrogen, and oxygen, then the mass of carbon plus the mass of hydrogen plus the mass of the oxygen should equal the mass of the sample. So now we've got everything with just one unknown. All we have to do is a little bit of addition and subtraction, and we'll have the mass of oxygen. The next three steps in our strategy will look really familiar because they will be exactly the same as elemental analysis. So we have grams of every element after steps 1 and 2. So then we can calculate moles of each element. Step 4, we can find the empirical formula. This is a combination of a couple of strategy steps from elemental analysis. And then 5, we can find the molecular formula if possible. All right, so these last 3, as I said, are same as elemental. Our example for this one says that vitamin C, which has a molar mass of 176.12 grams per mole, is composed only of carbon, hydrogen, and oxygen. A 1 gram sample is combusted and yields 1.50 grams of CO2 and 0.41 grams of H2O. Find the molecular formula. So step 1, we're going to get carbon from the CO2. We're going to get hydrogen from the H2O. So this will actually be a pretty long step, especially with the explanation since it's the first time we're looking at it. So what we use in combustion analysis are the mole ratios of an element within a compound that we talked about in an earlier video. So strategy-wise, we know grams of carbon dioxide. We know a way to get this to moles of carbon dioxide. And if we know moles of carbon dioxide, we can actually get moles of carbon because we know how much carbon is in carbon dioxide. And then we can also get grams of carbon if we know moles of carbon. I'm going to split up this calculation in a specific way that I recommend, but you are welcome to do it whichever way you'd like, as long as it's a valid method and you show all of your work. So one of the pieces of information that we're given is that our reaction produced 1.50 grams of carbon dioxide. And this was in an earlier video, so I won't explicitly calculate it here. But if you needed to, you could calculate the molar mass of carbon dioxide. And we know that 1 mole of CO2 is 44.01 grams. So we're at moles of CO2. From the formula, which has 1 carbon and 2 oxygens, we know that we get 1 mole of carbon for every 1 mole of CO2. And I'm actually going to cut my calculation off here and calculate that we have 0.0341 moles of carbon. And the only reason I'm going to do this is so we don't have to recalculate it later. So if you remember, when we get to the empirical formula part, we need to put our subscripts in moles. There's no reason to go past the mole calculation and then recalculate it when we've got it in here anyway. Now we do still have to go to grams of carbon because we'll need that to help find how much oxygen we have. So I do still have to take my 0.0341 moles of carbon and multiply that by the molar mass of carbon to find that my original 1 gram sample was 0.409 grams carbon. Okay, so I have 2 pieces of information that I'll need later related to carbon. I still have to find all of this about hydrogen based on the 2 products that I was given. So there are 0.41 grams of H2O collected from this reaction. If you calculate the molar mass of H2O, 1 mole of H2O is 18.02 grams. And then in my formula, it's 2 hydrogens and 1 oxygen. So I get 2 moles of hydrogen for every 1 mole of H2O. And I'm going to pause here. I'm going to put a big red box around this. I'm going to put a star by it. Put 4 stars by it. I 100,000,000% guarantee that if you are having trouble later in your empirical formula, you can't get things to whole numbers, you can't figure out why you got the wrong answer, this is the most common place that people make a mistake by not accounting for the fact that you get 2 hydrogens for every 1 H2O. It makes a huge difference in your answer. And these are numbers that you have to carry forward. So it's very important that you are careful with your mole ratios here to ensure that you get the right value. Okay, so if I multiply all of this through, it's 0.046 moles of hydrogen. Right? We're going to need this number later. But we also need the mass to the 0.046 moles of hydrogen times 1.008 grams per mole. My original sample had 0.046 grams of hydrogen in it. Okay. My molecule has carbon, hydrogen, and oxygen. Oxygen is the only thing that I need information about. So step 2 is getting the mass of oxygen. And so the question is usually, why can't we use the carbon dioxide and the water? And the reason is that in the combustion reaction, we added oxygen in order for the reaction to go. So let me get a different color here. We're going to say can't use molar ratios from CO2 and H2O because these two oxygens and carbon dioxide, this one oxygen in H2O, we don't know if that oxygen came from the original sample or the O2 that we added in order for it to do the reaction. The one thing we do know is that our entire sample is made up of carbon, hydrogen, and oxygen. So if I subtract the masses of carbon and hydrogen, everything else has to be oxygen. So this is why we do mass of carbon plus mass of hydrogen plus mass of oxygen equals the mass of the sample, and also why you need to know the mass of the sample in this case. So from step 1, it was 0.409 grams of carbon, 0.046 grams of hydrogen, plus, put this in a different color since it's what I'm solving for, the mass of the oxygen equals my entire sample was 1 gram. So if I subtract the 0.409 and the 0.046 from 1 gram, I'm left with the mass of oxygen being 0.545. Step 3 is to find moles of each element. And we've already done most of this. So within step 1, we got that carbon was 0.0341. Hydrogen is 0.046. And now we have the mass of oxygen, which is 0.545 grams, and we can calculate how many moles this is. And it ends up being 0.0341. Okay, so step 4 is to get the empirical formula. In order to do that, I first write a preliminary formula. So my carbon has 0.0341 moles, hydrogen is 0.046, oxygen is also 0.341. Now the 0.341 is the smallest number, so I'll divide through by that. And I get carbon 1, hydrogen 1.34, yikes, oxygen 1. So I got the numbers compared to each other, but I didn't end up with a whole number. So this is where you do the multiply to get whole numbers. So your empirical formula still has to have whole numbers. We can't leave it as these decimals or fractions. And honestly, the way to do this is kind of a guess and check method. So you could say, all right, so what if I double them? Then I would get C2, my H would be, like 2.7? That's still not a whole number, so that's not going to work. So then you try 3. If you multiply by 3, you get, carbon with a 3, and then hydrogen with a 4, or something really, really close to it. So that's good. So in this case, we're going to multiply by 3. So 1 times 3, 1.34 times 3, 1 times 3. So C3H4O3 is my empirical formula. there are some places in some textbooks that will tell you, like obviously if it's 1.25, you would want to multiply by 4. If it's 1.2, you would want to multiply by 5. So you can kind of get those math associations in your head, or you can do what I was describing, which is try 2. If it doesn't work, try 3. If that doesn't work, try 4. Eventually, you shouldn't have to go up, right? Like you probably won't go up as far as 10 in something that's an empirical formula. If you've gone up really high and you're starting to worry, go back and check your work on the earlier steps to see if you're ending up in the right place. Okay, now we do have the molar mass, so we can find the molecular formula here. So I need my empirical molar mass, which is 3 times 12.011 plus 4 times 1.008 plus 3 times 15.999, which is 88.032, which does not match, so I do need to divide. And my actual divided by my empirical, 176.12 grams per mole, divided by 88.032 equals 2. So my C3H4O3, I need to double all of those. So C6H8O6 is my molecular formula.